We have a great lineup for the next 2 hours. I'd like to introduce Jean-Pierre Thibault from the University of Bourgogne.
Yeah, you can say Burgundy.
Burgundy, thank you.
If you want a translation.
And the title of his talk is Why Do Students Fail to Learn and Use Central Science Concepts or Simple Mathematical Notions when Associations Dominate Reasoning? Thank you. Over to you, Jean-Pierre.
Thank you. So we are already late, and that's bad. That's good for me because in France, we have this reputation of being always late. So I found the worst. Yeah. Okay. So I have a broad schedule here. I'm going to cut into a little bit and shorten my things. So the main idea is that even though we can develop very formalized scientific concepts or mathematical concepts, most of the time they remain tied to word knowledge, to outside knowledge, things that have nothing to do with the domain itself, mathematics or science. So I'm going to tell you a little bit about math, science, or even morphosyntax. So in all these domains, competence could be described as the use of formal devices, relevant formal devices in the good situations. In mathematics, for example, when you solve a word problem, you have to use the relevant algorithms, whatever the objects and relations. I mean, algorithms do not depend on the objects and relation. I'm going to show you that it's not the case. In physics, if we refer to the concepts of force and energy, those concepts they work whatever the objects. I won't have the time to present this, but again, it's wrong. It's wrong. In morphosyntax, speakers they translate semantic relations, whatever the entities in the appropriate morphosyntactic devices, which means that we we're thought to be able to use morphosyntactic devices independently of the semantics behind. So my main hypothesis is that formal knowledge is influenced by word knowledge and sometimes the objects referred to in the problem. So let's start with syntax. So we have highly formalized devices, and learning of these formalized devices is to capture those formal regularities. So normally, if we have abstracted these formal regularities, we could be able to generalize them to an infinite number of situations. So it means that our syntactic algorithms, I may say so, are productive. I'm just going to give a short example with the passive voice and showing that it's not the case, especially for children. By the way, I am a developmental cognitive scientist, so I'm really interested by the way children build their knowledge. So in French, at least, but in other languages, passive voice is something which we could formalize it as a patient, who is verbed by an agent, whereas the active is agent verbs the patient. Okay, so as children, when children learn those syntactic cues, it happens that most of the time, at least at the beginning of their learning, the way they interpret the passive voice highly depends on the entities or the verbs used, the semantics of the verbs. Let's skip that. Okay, we did an experiment years ago on 3 to 8 years old children, and it happens that passive voice understanding, even though it's a very simple grammatical device, they need at least 5 years to completely understand how the syntax works, independently of the irrelevant semantic features. And what we found, for example, is that action verbs like to hit, if you build a syntax in a passive voice sentence with an action verbs, it will be better understood by the children than with cognitive verbs, which makes absolutely no sense given from a syntactic point of view, because something is hid by or somebody is seen by is exactly the same framework, the same syntactic framework, but not for the kid. Also, for example, semantically reversible passives, so like Mary is liked by or is seen by John, is a reversible passive, whereas a non-reversible passive would be the bottle is hit by Jean-Pierre, for example. And those passives with reversible, which are reversible, are more difficult than the non-reversible. So the reversible ones are more difficult than the irreversible. So you might think, okay, it works for kids, it's none of our business. But in adults, you can exactly show the same thing, but through reaction times. Of course, the adults won't do any mistake, but the reaction times will show that, for example, reversible passives will take more time to be interpreted than non-reversible. So the point is, my first point is exactly that. Even though we are supposed to be extremely competent, it's not a problem of not knowing, of incompetence. We are very competent with these syntactic devices, even though we are very competent. We tend to interpret them in terms of the features and the semantic features of the information, which are built in the information which is given by the words. Let me try now to illustrate it with algorithmic competence in mathematics. So everybody would agree with, we first come with arithmetics by learning algorithms, very simple ones, and we overuse them later on, like addition, subtractions, or division, or multiplication. So first we start with example, of course, and then teachers hope that they would become abstract, independent of the objects that were referred to when we learn those algorithms. That would be the intuition of any mathematicians, but in fact, it's not true. So to put it in another way, mathematical abstractions mean 1 + 1 = 2. 1 bird + 1 bird make 2 birds. 1 hour + 1 hour is equal to 2 hours. So computationally, mathematically speaking, all these situations, all these sentences, I may say, mathematical sentences are completely equivalent. I'm going to tell you and to show you that it's absolutely not the case. So the question is, does our knowledge about the world interfere with abstract mathematical reasoning? And I'm going to suggest that it's the case. It interferes whereas it should not be the case. Okay, I'm going to skip that. So the basic idea is that algorithms are associated with objects, and I'm going to demonstrate it with arithmetic problems which have 2 solving solutions. So there are 2 different ways to solve them. And the other thing that I'm going to demonstrate is that the chosen solution actually depends on the type of quantity. And in that research, which has been published with a PhD student, Hippolyte Gros, and a colleague from Geneva, Emmanuel Sander, we started with the distinction between cardinal and ordinal quantities. And here is what I mean by a cardinal quantity is to be thought as a combination of subsets, whereas ordinal quantities are more easily thought on a continuous axis. I'm going to show. So here is a cardinal problem and the way we would tend to encode it. So it's when I say we would tend to encode it, we have done the experiments and we know the statistics most of the people, most of the students, they would encode it in this way. So Tom grabs a Russian dictionary weighing 5 kilo, and is also carrying a Spanish dictionary. And then in total, both of them makes 40 kilos of books. Lucy takes Malik's Spanish dictionary and a German dictionary. And oh yeah, I didn't mention. Okay, here E is Malik, sorry. Lucy takes Malik's Spanish dictionary, so it's exactly the same Spanish dictionary as here, and a German dictionary. And the German dictionary weighs 2 kilo less than the Russian dictionary here, so 2 kilo less than 5. So usually we will compute this. So the question is Emily also? It's Lucy. I changed things in the morning and I didn't do it properly. So this is Tom and Lucy, and that's it. And there is no Emily there. Okay, otherwise it will become confusing. So everybody tend to solve, or most of the people tend to solve this kind of problem in the following way. They first compute 14 minus 5 to get what is the weight of the Spanish dictionary. So you get 9. Oops. 9, and then you come to Lucy, which has the same Spanish dictionary. So now you know that it weighs 9 kilos, and then she has a German dictionary which has 2 kilo less than the Russian dictionary. So you say, okay, that's 5 here. The Russian dictionary minus 2 equal 3, and then you compute the total. 9 plus 3 equal 12. And then we're another type of problem, what we call ordinal problem. Tom attended piano classes for 5 years. He started attending the classes when he was a child. Tom stopped attending the classes at the age of 14. Lucy, again, started attending piano classes at the same age as Tom. Lucy attended the classes 2 years less than Tom. How old was Lucy when she stopped attending piano classes? And it happens that most of the people here would tend to solve the problem by doing 14 minus 2, but what is 12? So what I didn't tell you now is that I exactly use the same quantities, and both problems can be solved in the same way. So it means that this solving procedure here can exactly be used here too. And maybe most of you did not notice, but maybe it's because of digestion. It's another problem. Okay, so we have 2 solving algorithms that work perfectly. And what I'm telling you is that we did experiments showing that in the ordinal case, most of the people are solving this way, whereas in the cardinal case, we tend to solve the other way. But as I said, both are available for both problems. Both solving procedures are available in both. So I can give her a more formal structure of the problem here, which gives cardinal quantities, and the people tend to, as I said, tend to represent them as, you know, potatoes, we say in France. I don't know if you say the same thing, words, sets. And here on the right, for the ordinal quantities as a continuous axis. And we did experiments also that I won't show you about, but I won't tell you about, in which we asked people to represent these things. And it's exactly what happened. On the cardinal quantities, they tended to draw potatoes, and when it was time, duration or age or number of floors, for example, they tended to use continuous axis. So it works. The idea seems to be relevant here. But now, suppose an experiment that we did. We propose the same problem, exactly the same problem, but with one missing information, which is the following here. So you cannot compute the 3-step solution here because you don't have the the 5 information is not given anymore. So given it's missing, the only way you can compute the solution is the one-step solution. So remember, you have 2 types of problems, one cardinal, which are going to activate the 3-step procedure, and you have the ordinal problems, which are going to activate the one-step solution procedure. So what is the prediction? The prediction is that people who would solve spontaneously cardinal problems with the 3-step solution will be in a trouble. And that's what is that. Whereas for ordinal problem, they would encounter no difficulty because the one-step solution is the one they would spontaneously go for. And okay, this structure of this experiment is a little bit, so here everybody would go cardinal 3 steps, ordinal 1 step. Cardinal doesn't work, so people should go, and that's the question, will they be able to go to rephrase, re-represent the problem and go to the one-step procedure. So we had adults, they were psychology students, and we had 6 problems which were solvable with the one-step algorithm and 6 of unsolvable problems which were just distractors. So the problem was not, could you find a solution? No, we gave them the solution. Do you think 14 minus 2 would work? So in both cases, when they are solvable by the one-step algorithm, they should say yes. Or for the unsolvable, they should say no. And here are the results. So for these participants, they were only 47% of the cases correct. I mean that in 53% of the cases, yes, okay, I will make it. In 53% of the cases, they incorrectly rejected this correct solution. I mean, does 14 minus 2 work? Equals 12. Does it work? They would say 50% of the time, no. And of course, the prediction for the ordinal would be completely different because the one step is the one they go for spontaneously. So they make much less mistake here. So you understand the point. It's not that people are making mistakes. It's the point is, given their representation of the problem, they will do mistakes exactly where we expected, which is exactly the same. So here we have another measure of their performance, which is response times. And you see for the cardinal, whereas the mean is here, is a strange way to represent it, but this is the mean time. And here you have the mean time for the ordinal problem. So to conclude, it means that they were less efficient in terms of correct answers for the cardinal, but they were also slower. So it was really difficult for them. And now let's talk about expertise, because you might always say, but they are psychologists. We know that psychologists are not very clever, and in mathematics, of course. And let's try with mathematicians, real experts. So if there is a difference, we cannot argue that the problems first were difficult, and then there was a lack of expertise. So exactly the same thing, except that we took our mathematicians coming from the National School, Superior School in Paris, which is the highest level in mathematics. If you know about the Nobel Prize in mathematics, which is the fifth medal, France got many of these medals, and all the people who won the medal came from this school. So it's really a high level school. So we had exactly the same problems, very simple problems. And as you see, they were better than the non-expert psychologists, but still, they were still answering 24% of the time that the solution 14 minus 2 equal 12 was not a correct solution. So they could not, that's the idea, they could not re-represent the problem, mathematical problems, in terms of another possible solution. And look here, exactly the same pattern as in the previous group, except that they were making less mistakes, but they are experts. But again, they do mistake. The errors were produced exactly where we predicted, and whereas they had virtually no error where we also predicted. And we got exactly the same profile in terms of response times. So what it shows that even experts reject correct solutions which are not compatible with their spontaneous encoding of the quantities. And the way this encoding is that one will really work. Or okay. Sorry. We have this one. Is activating the algorithms. So who said abstraction? No abstraction, even in mathematician. So my last example, I need 1 minute, so it's sufficient. Again, with experts, because I don't want people to confuse this with the idea of spontaneous naive theories. It's not that. They are real experts and they have been trained. So it's not that. Here we had real biologists. They were from Cambridge and from Harvard and Cambridge and from the Boston area. Very good experts. And very simple task: classify stimuli into living or non-living. So you just have to say, is a dog living? Yes, no. Is a car living? Yes, no. And there were 4 categories of things: animals, plants, non-moving artifacts, moving artifacts, non-moving natural kinds, moving natural kinds. Oh, by the way, it's not an experiment by me, it's an experiment by American colleagues, but I like it. And animals, no problem. They were students, and oh yeah, they were first student. Let's go immediately for the experts. Experts, biology professors, they have exactly the same profile than the students, except that they did less mistakes. But which mistakes? Again, everybody does mistake. No problem with that. The problem is that they rejected more plants than animals as living things, and they accepted more non-moving objects. They rejected more non-moving objects than moving objects, which is exactly what should be expected if you think about a very frequent association between animacy and living. So animals are animate, so there are more living things than plants. And artifacts which are moving, they are more associated with animacy, which means here in my experiment, which translates here in my experiments in the fact that in the result that they made more mistake for moving. And also they took more time to decide that plants were living things, and they took more time to decide that moving objects were not. Okay. I have also things on force and energy showing here, but it's exactly the same story. So what does it mean? Experts never totally replaces their former conceptions. So it's not a problem, as I said, it's not a problem of misconceptions. They have the correct conception. It's the problem, these are more the results of cognitive association that has been built during our learning, and it's even experts, they cannot get rid of these initial associations. Thank you.
Thank you so much, Jean-Pierre.